Thank you very much.
Okay, thanks for the invitation to speak in this on this occasion, and thanks for the introduction. So today's subject is particular Calabi-Yau degeneration, which I consider as strange. Now, this might be part of personal character, so if you don't find it particularly strange, then just cut that word, but then it degenerates to a Calabi-Yau degeneration, then I at least hope you might still find it an interesting Calabi-Yau degeneration. So it is work done jointly with Slavik Zink from Krakow, and it's part of my long-term interest in topological, geometrical, arithmetical properties of Calabi-Yau threefolds with small Hodge numbers. Probably an interest shared by many of you. And of course, the most extreme cases where you have H12, so the Hodge number H12 equals 0, then there's no infinitesimal deformations, and it's so-called a rigid Calabi-Yau. And then the Hodge numbers of the H3 of X, which then is two-dimensional, read 1, 0, 0, 1. So two ones from the holomorphic three form and complex conjugate. And so you get a two-dimensional space. And if X is defined over Q, then the arithmetic is interesting. You can look at the counting points on X for all prime numbers, combine it into an L function. And it's known that this L function is then an L function of a modular form, a weight 4 form for a congruence group gamma 0 n for some n. And so this is a theorem which developed out of the work of Wiles and automorphic lifting things, and was proven by Huey and Gouveia already some years ago. And but I still think the problem of characterizing which modular forms appear as L functions of rigid Calabi-Yaus is still wide open. So there are still a lot of modular forms which have no Calabi-Yau realization up to now. This is contrary to the case of elliptic curves, where every weight 2 modular form is known to appear for an elliptic curve defined over Q. The second part of my interest is Calabi-Yau manifolds, which H12 is one-dimensional, so these vary in one-dimensional moduli. And the Hodge structure is of rank 4, and all Hodge numbers are 1, and it varies in such Hodge structures can move in a one-parameter family, but we're outside the domain of the classical period domains. So these are sort of first very unknown types of objects. There is a speculation that the L function of such varieties always come from paramodular Siegel forms of weight 3, but up to now there is just a few examples. And this is a project which is starting to get going on with many people, with Vasily. He will speak tomorrow, Golishev, but I don't know if he will speak in particular about these things. Today I want not to speak about arithmetical properties, but rather focus on an aspect which relates these two types of varieties, the rigid ones and the one-parameter models. And well, the classical way these type of manifolds are related is by what is now commonly called a conifold transition. And the idea is rather simple. And the first example, as far as I know, appears in Chad Schoen's paper where he looked at the variety here called X1, sum of 5 fifth powers equal to 5 times the product of product of the variables. And this is a variety to be considered in P4. Let me here. So this variety is a quintic in P4, and it has 125 nodes, and you can find a small resolution, a crescent resolution, and then after resolution, you get a Calabi-Yau manifold, which has H12 equals 0. It's a rigid Calabi-Yau, and that can be understood from the perspective of Friedman that the deformations of X1, a singular variety with 125 nodes, which keeps the nodes, is the same as the deformation theory of X itself, because the contracted P1s are stable manifolds, and there are no deformations of this hypersurface which keeps all the nodes, therefore it's rigid. But of course, there are deformations which smooth out the node, and this is part of a famous pencil, the Dwork pencil, where you introduce a variable, you replace the 5 by 5 psi, where psi is any parameter. And if psi is not 1, you will smooth out the 125 nodes. And then you have a variety, which the smooth variety, which degenerates into the singular one, which after resolution then becomes the rigid one. And this, so you see this one parameter family degenerates into a rigid variety. And the conival transition consists of contracting in S2, the 2 sphere, or the introduced P1 of the small resolution. In this example, 125 copies of them. You get a node of dimension 3. It does not look quite like in this picture because this is a 2-dimensional picture, but you cannot draw a high dimensional. And then by smoothing, you get the cone, you get a vanishing 3 sphere. So this is very well the geometrical transition. You change the Hodge numbers, and in this way you can expect to have in one parameter families of Calabi-Yau manifolds singular members whose resolution is rigid. And this is what happens here. In fact, Chachern was also the first to determine the L function of such of this variety X1 or X, and found it was given by a modular form, determined by a modular form of level 25, gamma 025. So now to understand a little bit more about what I'm going to tell, let me recall some basic facts about degenerations and limiting mixed Hodge structures. So I've here drawn the classical caricature of a family of varieties with degenerations. It's a family of P1. For the moment, it's just general of, it will be a smooth map. Fibers in general will be smooth varieties XT of dimension D. And then there is a finite set of points where we have degeneration. And then we first can form the local system of cohomologies on the open part, U, where the map is smooth. And then, of course, the fiber of the local system, HT, is just the D cohomology of the variety. And if you vary the parameter T over the line, you get what is called a variation of Hodge structures. And in the examples where I'm interested in, it's a variation of Hodge structures with Hodge numbers 1, 1, 1, 1, as I mentioned before. Now, this leaves out these special points where you have a degeneration, these red points, but it is a very classical result that one can sort of complete this family over the open part by adding for each singularity, each point of this set sigma, so-called limiting mixed Hot structure. So the Hot structure becomes a more complex object, more complicated object, called a limiting mixed Hot structure. So, and that depends only on the infinitesimal neighborhood, first, in fact, just first order neighborhood of the point of the family. It's usual to pick a disk and restrict the whole family to that disk around the singularity. And then you have a situation of a degeneration. And then the most basic topological invariant is the local monodromy. The local monodromy, if you go around the singularity, for that I pick a base point T0 somewhere near the degeneration variety, degenerating variety. And now the so-called monodromy theorem says that this transformation is quasi-unipotent. So after a finite base change, if you replace the local parameter by power of it, the monodromy becomes unipotent. And then one takes the logarithm of the the monodromy minus the identity, the monodromy logarithm. And this is a most important cohomological invariant of the degeneration. In fact, the limiting mixed Hot structure consists of a vector space H, which can be taken as just the ordinary, the cohomology of a fiber nearby degeneration point. Then you can take, it has a limiting Hot filtration obtained by taking a family of the ordinary Hot filtrations and then taking sort of the limit for the point T go to A. And then this monodromy N produces an extra filtration. This is the weight filtration on the cohomology. And the graded pieces are pure Hot structures. But this weight filtration is completely determined by the monodromy action. And it's characterized by this fundamental isomorphism that the GUR graded piece D plus K of the limiting mixed structure is isomorphic to GUR W D minus K of the limiting mixed Hot structure. And the map is the nth power of the monodromy logarithm. This uniquely fixes the filtration W, and it's called the monodromy weight filtration. And it's a very deep fact that the monodromy weight filtration, which is sort of purely topological, if we grade with respect to that, we obtain pure Hot structures. So this is the basic discovery of Schmidt, and was then elaborated in the geometrical case by Steenbrink. This is in the 70s. I think this was in 1976. And now, so this is the most important invariant of the degeneration, and as a cohomological, on the cohomological level. And now there is fortunate fact that one can, in practical situations where one can calculate things, we can obtain the Jordan structure of this map N from the corresponding Picard-Fuchs operator. So we know this Hot structure can be described in terms of period integrals of this family. So we take a differential form, integrate over a cycle in the fiber, we get a multi-valued function on the base. It's annihilated by a certain differential operator. And this is called the Picard-Fuchs operator. So it depends on the family, of course. It depends on the choice of your differential form. And then you get a unique differential operator. And for example, for the mirror quintic, which is in fact closely related to the family we had here, where Chad shown in the dwarf pencil. So here, the cohomology of the general fiber is 101 dimensional, but then one takes invariance for the group, and then for the group of order 125, then you get the mirror quintic, and then you get such a 1111 variation. And the Picard-Fuchs operator is very well known. It's a celebrated form written down. It's a hypergeometric differential operator. Theta is the logarithmic derivative with respect to the parameter t. The parameter t is just expressed in terms of the parameter which was formerly called psi. And then you have this fourth order differential operator, which annihilates all the period integrals with respect to the holomorphic 3 form on that family. So there is a specific choice you have to make, of course, for this differential form, but then you find this differential operator. And if you want to understand a differential operator, you first look at so we're then very much in the classical 19th century theory of linear differential equations in the complex domain. And you look at the Riemann symbol. And here you see the Riemann symbol of this operator. It starts with theta to the power 4. So the characteristic polynomial of the polynomial theta to the power 4 has is defining the 0 with multiplicity 4. So the exponents in the origin are all 0. It means that the solutions, there is a basic set of solutions to this differential equation, which first solution starts with 1, the next solution starts with a log t, the second solution a log squared of t, and then a solution log cubed of t. This is all very well known. And then at this point, 1 over 5 to the power 5, this is the point where the conifold transition appears in the story I told before about Chad-Schoen. So here's where you find the Chad-Schoen variety. And there you see there are 2 exponents 1 and 1 exponent 0 and 1 exponent 2. And it means that it appears that there is a solution which starts with a constant. There is another solution which starts with t. And there is a solution t times log t. And then a solution which starts with t squared. The appearance of such a log I've indicated with this hook, these hooks here. And now the rule is that any appearance of the log t gives an n. So here we have log, constant log, log squared, log cubed. This means n cubed. The operator n cubed is non-zero. And here we have an n, which is in the conifold case, we have n, but n squared is 0. At the point infinity, the monodromy is a finite order. The exponents are 5th, 2/5, 3/5, and 4/5. And there are bases of solutions, very special solutions, which have this power series expansion in T, which starts like that. From this, you see that the monodromy around that point is of order 5. And the monodromy around this point, this is called the MUM point, the maximal unipotent point, is of course infinite, but also the monodromy about the conifold point is also infinite due to the logarithm. So now now I will start writing here. So now in the process of degeneration of Hodge structures, if you start with Hodge structure with all numbers 1 and you go to a mum point, then these ones you had originally get teared apart and becomes ones like this. Maybe use another color. So after, if you go to the degeneration, the origin, you get this, and the there is a N, maybe remove this. And okay. So originally there were the zeros here, but now due to the degeneration process, these in the limiting mixed Hodge structure, these ones move. And here we were in weight 3. I will draw the weights here. But now we get weight 4 and weight 6 and weight 2 and weight 0. And the N is moving downwards. So this is this Jordan structure. And you see very clearly that it is complete reflection of this solutions, but you can also sort of see it in the Riemann symbol. And the same for the conifold point, where if you start with a Hodge structure with these Hodge numbers, and now you degenerate towards the conifold point, the Hodge structure becomes mixed, and now only 2 ones get shifted. So you get a Hodge structure where you have, this is the weight 3 part, W3 is of that part, and the graded part of degree 4 is this one, and below is this one of degree 2. So it's very easy to see what happens. If there is orbifolds, if the monodromy is finite order, then the theory of mixed Hodge structures tells you that the N is 0, the N operator is 0, and the Hodge numbers stay, I've just put as they were in the smooth case. So you just get this, but if you then degenerate to infinity, then the Hodge numbers stay just where they were. The operator N is just 0. And the Hodge structure stays pure. And here we get a non-pure. So here you get an extension of Hodge structures. And here in the mum case, you get an extension of just ones. So here you get an iterated extension of Tate motifs. Here we get an extension of a motif of weight 3 with 2, with 1 a little bit higher and 1 lower weight. So this is the standard picture. And if you look at other families of varieties, of Calabi-Yau varieties, then the way in which a smooth variety specializes to a rigid variety always goes via this scheme. So this conifold transition scheme. The variety not necessarily has only double points as singularities. It might more complicated singularities appear, but you always will have an n, which is non-zero. And in the Picard-Fuchs equation, you will have such a type of exponents. So you get two repeated exponents in the middle. And it came somewhat as a surprise that there is another possibility. So this is the strange degeneration, which I now want to explain. So this is the theorem. So there exists a family of degeneration with y smooth. The dimension is 3, 4, and fibers Calabi-Yau. So with okay, so this is projective map. Yeah? Projective. For t not equal to 0, yt is the fiber t is a smooth Calabi-Yau threefold with H12 is 1 and H11, well, it's not important for this talk, but the example I speak about, it's 41. And for T is 0, the 0 fiber has a double line of singularities. And if we blow up that line, we get Z0 is to blow up on line L. Is a smooth Calabi-Yau with H12 is 0, H11 64, 46. And so this is it. And now the main, what makes it trivial, the monodromy, well, is trivial on HI, I not 3, and of order 2. Finite, so in particular, it's finite order on H3. So a corollary, or what comes out of this family, is that you have that the limiting mixed dot structure, lim, of this family is consists of H3 Z0 plus direct sum H1 of an elliptic curve twisted once. So it's a pure but split structure. and where E is 2-to-1 cover of L ramified at 4 points on the line L. So it's just a double cover of well, maybe use the ordinary picture. So we have just 4 points. Double cover of that line.
Hi, Duco. Duco. Yeah. I was just wondering, is this the picture in Pelham-Wilson's work where you have these elliptic ruled surfaces that play the role of -2 curves on Calabi-Yau free folds? In terms
no, it is different because here you get the monodrome is trivial, and you get a
finite order. I thought you said as a reflection. I think in Pelham's work it was like the vowel group that shows up, like you know, like the vowel group for K3s. You get like reflections. Is that what you're talking about?
No, not really. Let me. But it is closely related. But so the J invariant is 1728. So why is this? You see, the difference there is that you have a family of Calabi-Yaus, which develop a elliptic ruled surface. So you have a family of varieties where the cohomology is just the same. Topologically, nothing is happening there. But here there is a big topological change because we have a rigid Calabi-Yau here at the origin and with other Hodge numbers. So what happens here is that this is just shows how different this is from the case of K3 surfaces. So remark, for K3 surfaces, there is nothing similar because if you have a K3 surfaces and you have monodromy finite order, this is called type 1. Then you have this Kulikov and Persson, old work, Pinkham. Saying that if the monodrome is finite order, then by modification, the zero fiber, so if we have a K3 degeneration, by modification, the zero fiber is smooth. But no such thing can happen here because the Hodge numbers are different, and so there is no way in which this can appear in a topological trivial family. This theorem of Kulikov, Persson, Pinkham is generalized by Collar, Lhasa, and Saka to hyperkähler manifolds of high dimension. And there, an analogous theorem holds that if the monodromy is finite, then you can modify by blowing up and down, you can achieve that you have a smooth family. Here, there is no hope that you can do that. In fact, if you look at our family here, so we have this family over the disk, and now we blow up over the origin, blow up that line, then inside here we have y0, and then we have the strict transform, which is here. And here is this line, and this line now becomes a conic bundle. No, a quadric bundle. Well, the plus P. And then if we make a base change of order 2, you have a manifold here. And this maps to and this maps to the line, pre-image of the line. Sorry. So this is a divisor with normal crossing. So a reduced divisor as this normal crossing. Reduced divisor with normal crossings. Here, of course, the multiplicity of the divisor P is 2, but by taking a quadratic pullback, and these two components intersect, and the second component takes half of the cohomology. This carries the cohomology of this E, this elliptic curve, and the other component carries the 3 form. So the space is split in 2 pieces, and this is unavoidable. There cannot be any pure smooth filling of this family because of the Hodge numbers of Z0, and the Hodge numbers are birational invariant, so it can never happen. So this is what we found strange, and the way we discovered it was by a study of a class of manifolds, which are called, so I'll give the example now, it's double octics. So this is sort of the simplest class of Calabi-Yau manifolds. You can make an elliptic curve as double cover ramified over 4 points. You can make a K3 surface as a double cover of P2 ramified over a sextic. And you can make the simple sort of Calabi-Yau manifold by taking a double cover ramified over hypersurface of degree 8. And in general, well, this is a large family. You can vary this polynomial F8, but then there are what I call special double octics. Where you require this octet to decompose in a product of 8 linear forms. So if they are generic, if in the generic case, you find 28 double lines, just each pair of planes, and then there are 65 triple points. And of course, now the double cover is singular, and there is a crescent resolution. There exists a crescent resolution. You can obtain it by blowing up the double lines in any order you like, and then taking the double in P3. So this is mapping to P3, and then do the blow-ups in P3, and then take the double cover. And here you have to normalize. And then in this way, you get a crescent resolution of the singularities of this singular space. And so you get Hodge numbers for that Calabi-Yau is H11 is 29. You introduce 28 extra devices, and H12 is 9. 9 planes depend on 8 planes depend on 9 moduli. Now you can also look at very special double optics by taking the planes in special positions, so not in generic position. And of course, there are many cases to consider. There exists still a crescent resolution if no fourfold points no fourfold lines, sorry. So you can allow 3 lines passing through 3 planes passing through a line, but no 4 and no 6-fold points. No 6 planes intersecting in 1 point. And then if you have these conditions, then, so this is a result by Slavek-Zink. He showed this. And this is necessary and sufficient for having a crescent resolution. And then Christian Meyer, in his thesis, in 2005, make large lists of, I think, 450 cases of all the different intersection patterns what can occur. And there are 11 cases where H12 is 0, so there are 11 rigid configurations and 63 cases with H12 one parameter families. And to give an idea for how these may look. So imagine a cube. So this is already 6 planes. And now add 2 further planes like this. So we take the diagonal in the down, in the bottom square, and then let these planes, 2 extra planes pass through the points here. So this is has a crescent resolution, and it will be a rigid Calabi-Yau, because you can show in general that the moduli of the variety correspond exactly to the moduli of the configuration. So if you change the topological character of the configuration, you change the Hodge. It's only a flat deformation of the crescent resolution if you have a deformation of the configuration. But you can, of course, deform the configuration where the combinatorial character changes. And you can, for example, move this point so that it no longer goes through the, you can make it, it's difficult with these colors. So you may just tweak this point, put it a little bit lower, but then now it's a configuration of which has h12 equal 1. So, and then by specializing the position, you get a variety with h12 equal to 0. And in this way, you have, in principle, very combinatorial way of understanding some interesting families of Calabi-Yau manifolds. And the example, we found our example in one of these examples of these sort. So we took number 153 from Meyer's list. And well, I can write down the equation. Maybe that's the best to do. So x, y, z, x plus 2y plus z plus tv plus v, y plus z plus v times x plus y plus z plus t minus 1 times v. So the variables are x, y, z, and v are the coordinates for P3. And u is the variable for the double cover. And so it's the v is just a homogenizing variable. And this is a configuration which has one triple line, L, and you can see it's x is 0, y is 0, x plus y is 0. Of course, this is the way it was set up. And then there are also 4-fold points on the line and 6 4-fold points not on the line. It's rather complicated if you, well, you have a completely explicit equation, but to understand what is going on is not so simple. But it appears that there are two planes. These are the planes Z, and given by these factors here, the fourth and the fifth factor in this product. And what is happening in the degeneration is that this is the triple line, L. And now for t is 0, there appears an extra, a 5-fold point. So you move this up, and now there is only 1 point. This is the degeneration which happens for t equals 0. T is 0. So now you have the non-trivial task of understanding the algebraic geometry of this variety, but miraculously it can be done, and it leads to the description I gave in the theorem. What is maybe most non-trivial to see is what is the monodromy and how to determine the monodromy. And what we do is we compute the Picard-Fuchs equation. And although this whole setup is given by simple linear equations, the Picard-Fuchs equation is rather complicated. But let me give you the Riemann symbol. So it appears that there are 4 special positions. So 4 special singularities, which by the choice of our coordinates are located at the point 0, 1, 2, and infinity. And then the exponents are as follows. So this is complicated, but it can be computed, and from the specific Picard-Fuchs operator, you can compute the Riemann symbol and the solutions and look where are the logarithms. The logarithms, I explained, they determine the type of the Hodge type of the degeneration. And it appears that in these blue brackets, you find a logarithm. I make here a writing error, 3/2. Now, from the classical theory of differential equations, there can be a logarithm if the exponents differ by an integer. Here the exponents are 1/2 and 3/2, so there could be a logarithm. But now this sort of the surprise, our surprise. When we computed the solutions around 0, which of course all can be done with a computer easily nowadays, 1 plus t. So they find power series, and you find this one corresponds to this one, and this one corresponds to this one. But you see, there is no logarithm. At 0. So this is the important thing. It means that the monodromy, well, you have your square root behavior. The monodromy is order 2, and the Hodge structure remains pure. And so it shows that this sort of type 1 degeneration of Calabi-Yau threefold is not sufficient to control the topology. You can have that the variety sort of splits in 2 pieces, and there is a rigid Calabi-Yau, which is the blown up of the variety Y0, which is of totally different topological type. But if you add to it this divisor P, then it smooths to the original Calabi-Yau, but there is no monodromy happening. So this is fundamentally different from what happens at K3 surfaces. And this is why I think it's a surprising or strange degeneration. So I see I'm already over time. So maybe I stop here, and maybe there are some questions we can. So I stop here.
Are there any questions?
Hey, Duco, you said something like if you deform the hyperplanes in an equisingular way, that corresponds to deformation of the Calabi-Yau, the resolution.
Right. That's very right.
You know, you have this kind of BTT theorem, and on the other hand, you have this Menev theorem that tells you if you have hyperplane arrangements, the deformation theory is really nasty. So how does that work?
It is quite interesting to look at these deformation spaces. So you find in the examples here, of course, Mnioff's theorem, it's talking about, in fact, lines in the plane, but many, many lines. And then it's sort of universal. You can get anything. But here,
I seem to remember there was the case of the octahedron in P3. It had some bad property, I think. I'm not sure if the 8.
Okay, maybe. But look, remember that there is no 6-fold points and no 4-fold lines. So probably that, I will have to look at that example. I don't remember. But so here in the examples, you find as one parameter families, just lines, P1s. Although a priori, there's no reason why it should be P1s. So you get really pencils. And in higher dimensional, I don't know. I mean, the moduli space, the two-dimensional moduli spaces are probably more complicated. But I find it surprising. I mean, you always want to have something which is computable and explicit, and then you have it explicit. So we have an explicit equation here. I wrote it down. And then you sit down and try to understand the geometry of this thing. It is damn difficult.
I was also wondering, you know, like from the point of view of the minimal model program, I don't think it's correct to be looking for a smooth fiber here. Maybe you're supposed to look for a fiber with some sort of mild singularity. Do you know what I'm talking about? Like,
well, but this is an honest reference resolution. I mean, of course, you may choose to leave the variety Y by itself, not resolve it.
Could you tell me again, like when you have the variety Y, like what is the is it like just a transverse A1 along a curve? Is that how it is? And then you blow up?
Yes.
Oh, okay.
Yes.
Yeah.
But then you must know that your cohomology of your space is the cohomology is disappearing, is the degeneration. So if you want sort of to extend period maps, then you're lost because you no longer have a 4-dimensional space in the cohomology space. If you want to have a form, so I think it's good to blow up, and then you get and look at the limiting mixed dot structure, and it has just 2 pieces, but the second piece is blown down. In that respect, it reminds you of this such an elliptic surface which you can contract and then smooth. But if you start with this thing where you have an elliptic surface and contract the elliptic surface and then smooth it, then the beginning and the end are diffeomorphic, because that's really based on the simultaneous resolution of double points in dimension 2. Right? This simultaneous resolution after base change, just crossed with an interval. This is what happening transversely. And here it's different.
You had this elliptic curve in the picture, which was like a double cover of the line.
Yes.
And I don't know, yes. I was wondering where that came from. And I wondered, you know, the first thing that occurred to me might be that you have, instead of like a P1 bundle over this line, you have like a conic bundle where every fiber is reducible.
You have a conic, you have,
and then you have sort of 4 double fibers. Is that the picture?
Yes, that's right. Yes, yes, that's what happens. But
you know, in Pelham's work, there was this case that was missed originally, where you have like a double a P1 bundle over an elliptic curve, but then you had like this sort of guy which had a line pair over every point, and then it was sort of twisted. I mean, Pelham can probably.
Oh, could I ask, when you blow up this this line, what happens to the threefold? does it have nodes?
No, if we blow up the smooth line, no, it becomes smooth. So after one blow up, the H3, the singular threefold just becomes a smooth, rigid threefold. It's a rigid, the resolution.
So what happens to the, I mean, what's the surface you get lying over the curve?
Over the line. That's a phonic bundle with 4 degenerate fibers. We get just 2. And then the nice thing is you can work out the cohomology in all different ways by sort of from the point of view of smoothing, and then it just works. You can determine all the maps. So there is no choice, or usually in a cohomological study, you have some map which you have to guess what it is. But here everything pans out. All the maps have to be 0 by weight or are isomorphisms. Just very remarkable, I found. So all the spectral sequences I could compute, it all worked out. You have the monodromy spectral sequence coming from the mixed watch, the degeneration based on the component and the intersections and all that. You get at a sanity check. But it might very well be that this type of degeneration has been noted before, but I could not find it, and people didn't know about it. And it is just a very strong example where you see that the K3, the Kulikov theorem, cannot be extended to the Calabi-Yau case. Of course, there are Calabi-Yau threefolds with terminal singularities, like an A2 singularity, and where the monodromy of an monodromy of an A1 singularity dimension 3 is infinite dimensional, is infinite, but the monodromy of A2 is of order 6. So there is this paper by Friedman, Clemens, and Morgan, old papers where they discuss this. And you can also not, so you get finite monodromy, you cannot make it fill a smooth in. And this is from the minimal model point of view, indeed, where you would say, well, we don't need to resolve this singularity, just let it be. It's a harmless singularity, but this is quite different.
Any further
So maybe I unshare. Stop. Maybe we can stop this.
Recording in progress. So our next speaker for the day is Paul Hacking, and he's going to tell us about mirror symmetry for Q-Fano threefolds.
Hi everyone, thanks very much for the invitation. It's a pleasure to speak here. So I wanted to talk about a work in progress with my graduate student, Christian Rodriguez. He's a graduate student at UMass. Basically, I've been following the Fano search program for a number of years, and I, when I was growing up as a grad student, I heard Miles talk on many occasions about classification of Q-Fano threefolds and sort of open problem, trying to understand those. That classification, which is part of the classification of algebraic varieties coming from the minimal model program. And the basic idea of the Fano search program is to try to leverage mirror symmetry for Fano varieties to help classify these Q-Fano threefolds. So just to give a sense, I mean, the case of smooth Fano threefolds is due to Q-Fano himself and Iskowski in the, I think, the 70s. But the case of Q-Fano is where you allow quotient singularities of a certain type is much more difficult. There's a very large number of deformation types, and there's a sort of list of numerical candidates prepared by Miles and others using Riemann Roch and other tools, but we really don't know which of those actually occur. We have lots of examples. We don't have a kind of definitive classification. And I think it's, of course, that will not be, we won't have one at the end of this talk either, but I'm just trying to explore, using what I know about mirror symmetry, what we should be looking for. And so, as I said, it's very much work in progress. I will value any comments or questions you make, so please don't hesitate to interrupt me if you have a comment or question. Having said that, are there any questions before I begin? All right, let's get started then. So Y will be a Fano threefold to begin with. So smooth projective variety such that the anti-canonical divisor is ample. If I take a general section of the linear system, the anti-canonical linear system, that will be a smooth K3 surface. And then the pair consisting of the Fano variety together with the divisor is an example of what we call a log Calabi-Yau variety. So that means that Ky plus the divisor is equal to 0, Y is smooth projective, and E is, well, in general, will be a normal crossing divisor. Here, it's actually a smooth divisor. And so this is supposed to be the sort of correct non-compact analog of a compact Calabi-Yau, to which mirror symmetry seems to apply with some minor modifications. So, the Strominger-Yau-Zaslow conjecture has a meaningful formulation in this context, and that was explored by Denis Roux and others to argue very convincingly that was possible. Okay, and so the question is, okay, so given such a Fano, well, what is its mirror? And, of course, historically, there was the notion of a Landau-Ginzburg model, and this is a sort of slight refinement of that. So actually what we consider is another log Calabi-Yau. So this time it has a function, a morphism to P1, such that D is a fiber, the boundary is a fiber. And so in particular, it tells you that this is actually a K3 fibration, just using the junction formula. And so secondly, the limit at infinity is what we call a maximal degeneration. So there are various ways of saying that. One way to say it is that this boundary divisor has a zero stratum. So this is the opposite case, where it's a normal crossing divisor, where it really has a vertex, a zero-dimensional stratum. Or, in terms of the, I'm just going to go into full screen here. In terms of the terminology of K3 degenerations, this divisor D is a type 3 K3 in Kulikov's classification. So I like to say it looks like a soccer ball, where the panels of the soccer ball are log Calabi-Yau surfaces, so something a bit like a toric surface with its toric boundary. Okay, so that's the mirror. So we're interested in trying to classify these objects, these particular K3 fibrations. So I want to develop a little bit more about what we expect about this fibration. And so all of this, these mirror symmetry heuristics come from a form of the Strominger-Yau-Zaslow conjecture, which is that the open parts of these manifolds, so the complements of the divisors, which have a holomorphic volume form, so this log Calabi-Yau condition says you have a holomorphic volume form on the interior, which has a simple pole on each boundary divisor. It gives you some kind of control at infinity. So those interiors have the dual torus vibrations of the special Lagrangian torus vibrations, as usual in mirror symmetry for Calabi-Yau free folds, or at least as conjectured by Strong and Zhihao Zhao. And so some of the consequences of that, oh yeah, maybe I should also say that in this picture, what happens as you go to the boundary divisor is completely analogous to the picture where you have the moment map for a toric variety, where the fibers over the interior are half-dimensional tori, and then they collapse to tori of dimension 1 lower at the boundary, and so you get sort of an induced Lagrangian torus vibration on the boundary divisor. So it's this kind of toric picture that the fiber dimension drops as you go to the boundary, and you get compatible torus vibrations. Okay, so one way to make mirror symmetry a precise mathematical statement is the homological mirror symmetry conjecture of Kontsevich. And so in this context, we have the following assertion. So you have the derived category of coherent sheaves on the Q-Fano variety Y, and then you have the restriction map to the derived category of coherent sheaves on the K-free surface E. And we also have this functor, endofunctor, functor from the K-free to itself, just given by tensoring by the line bundle, which is the induced ample line bundle on the K-free, so minus KY restricted to the K-free. So that's sort of the complex side for the Q-Fano. And then, according to these standard conjectures, that is equivalent to, on the K-free fibration XD, we have something called the Fukaya-Seidel category for the total space over the affine line. So remove this boundary divisor. And so there, I mean, I would say the details are a little bit delicate, but the Lagrangians one considers in this type of Fukaya category are the so-called left spimbles traced out by vanishing cycles for this pencil, with boundary on a fixed reference fiber. And for this category, we have a restriction map to the Fukaya category of the general fiber on this pencil. And that this map just takes a left-step spimble to its boundary. We have an action there of the monodromy around the point at infinity on this Fukaya category. So if you have a family of symplectic manifolds, then the monodromy transformation is not just a diffeomorphism to homotopy, it actually has it's a well-defined symplectomorphism once you've chosen the symplectic structure on the fibers. So that's why this gives you an action on the Fukaya category, which is a symplectic invariant. And I should say, you know, because I'm making a lot of assertions here that are conjectural, this picture is essentially completely worked out for the case of Delpexo surfaces in the paper of Aru, Katsakov, and Orlov from 2006. So that's a really good reference if you've never seen this before. Questions so far? Okay, yeah, and so I probably should have mentioned this, that here in this picture, we understand that we fixed the complex moduli YE, so the complex structure on YE, and that corresponds to a choice of complexified Kähler form, so this B field plus I times the Kähler form on the mirror, so the K3 fibration. Okay. Okay, and then so one other thing that is in this picture is sort of now reversing the roles. So there's sort of two halves of mirror symmetry where we consider one side as complex and one side as symplectic and vice versa. So if we sort of switch the roles here, we would have an equivalence of the derived category of coherent sheaves on the open part of the K3 fibration. And that is supposed to be equivalent to what's called the wrapped Fukaya category of the open part of the Fano. And, you know, so I don't want to say too much about the wrapped Fukaya category, except that this is just a version of the Fukaya category for certain non-compact manifolds where you allow certain non-compact Lagrangians with controlled behavior at infinity. And you also have to modify the definition of morphisms in the Fukaya category for those non-compact Lagrangians. But anyway, we have this equivalence here conjecturally. And again, this equivalence in the case of del Pezzo surfaces is now established by work of Keating in the hypersurface case and myself and Keating in the general case. And so here, I think it's important to mention this sort of asymmetry, that here we want to just consider the given polarization minus K on the Fano Y. And so that gives us a distinguished Kähler form on the interior, which is exact, because remember, E is a section of minus Ky. So the Kähler form is exact on this open part, d theta for some one form theta. And we take the trivial B field. So the symplectic structure now on Y minus E is completely determined. And so therefore, on the mirror side, the complex structure on X should be completely determined as well. So we have a distinguished pencil of K3s associated to a deformation type of Fano threefolds. And also sort of in the same vein of reasoning, if we were to vary the choice of complexified Kähler form on Y, that would correspond to a deformation of XD, of this K3 fibration. But in the case, which is the most important case, where B2Y equals 1, so the Picard group of Y, the Fano, is isomorphic to Z, then there are no such deformations. So the Moser theorem tells you that these Kähler deformations correspond to just the class of the complexified Kähler form. So here, the corresponding group is 0, so there are no deformations, at least none coming from mirror symmetry, which conjecturally is everything. And so we expect that this is a rigid K3 fibration over P1. Okay, so those are some sort of basic assertions about this mirror correspondence, which, you know, are not really new. These are sort of known, I think. So I'm just reviewing work of others mostly, especially Aru. Okay, and so that's kind of the setup, and our problem is I would like to describe this mirror of a complex mirror of a symplectic Fano as explicitly as possible, and hopefully use it as a tool to classify Q-Fano threefolds. Let me see. There must be a question by now. Are there any questions? I can't see anybody. Okay. Well, okay. Is anybody there?
There's no.
Yes.
Okay, good. It's getting a bit lonely here.
There's no questions from the audience in Warwick, so
Yeah.
we're all happy so far.
I think I need some more jokes. Okay. All right, but anyway, let's sort of dig into this a little bit. What I want to basically, there's like one idea in this talk, basically. Well, there's a couple of ideas, but the main idea is how does this picture change when we replace the Fano variety by a Q-Fano variety? Because, as everybody knows, Fano varieties, Fano freefolds have been completely classified, but Q-Fanos, that's a big open problem. So let's kind of think about that. And the nice observation somehow is that actually, you know, it's pretty minor, the modification. And so maybe if we know where to look, this is going to be a useful tool. So let's review why we have this maximal degeneration at infinity in the K3 vibration. So why is it the case that we get this type 3 degeneration at infinity? And you know, one way to say that actually is that that degeneration is supposed to be asymptotic, but not sort of on the nose, equal to the sort of mirror of the sort of large volume limit when you take this K3 on the Fano E, and you take the Kähler form, but then you sort of scale it, let it go to infinity. That's supposed to give you this maximal degeneration. That's sort of the usual picture, of course, in compact Calabi-Yau mirror symmetry for what happens, why these you know, large complex stricture limits, maximal degenerations of Calabi-Yau are so cool, because they correspond to this large volume limit on the mirror, symplectic mirror. So that's sort of why, from a sort of broad strokes point of view, but let's also discuss it from the point of view of homological mirror symmetry. So remember, we have this equivalence between the Fukaya category, the general fiber, the K3 vibration, remember that's called F, and the derived category of coherent sheaves on the K3E, the section, anticanonical section of the Fano. And so we have this monodromy action. So T is going to be the monodromy around infinity, acting on the numerical K theory of the Fukaya category, which is just a subgroup of the second homology. And you send, so here, a Lagrangian, possibly decorated by a unitary local system. You just send that to the rank of the local system times the class of the Lagrangian in homology. And that's mirror, as we said, to the action of the line bundle, the polarizing line bundle on the K3E by tensor product on the numerical K theory of coherent sheaves on E, which is just identified by the Chern character with the PP cohomology of E. And now it's sort of obvious, just by the formula that the Chern character is multiplicative, that in the second case, that's a unipotent action given by a unipotent matrix. And so therefore T should also be unipotent. And in fact, maximal unipotent in the sense that its cube is 0, but its square is not 0. So here, it's just a general fact that the highest power is the dimension of the variety plus 1. Oh yeah, and let me just say, if you were wondering, what about the cohomology that's not seen by the Fukaya category, so the cohomology that's not seen by Lagrangians? Well, so the sort of orthogonal complement of that is actually going to be just the image of the Picard group of the total space of this K3 vibration on the general fiber. Or in other words, it's the monodromy invariant elements of the Picard group, or the second cohomology, in fact, of the general fiber. So let me sort of briefly explain this. So the first thing you need to know is that because XD is a log Calabi-Yau, there's a theorem of Collar and Shu that because it has this maximal boundary, so boundary of a zero stratum, it has to be rationally connected which in particular implies via the exponential sequence that the Picard group is topological. So the first Chern class is an isomorphism. So then if we choose a sort of general complexified Kähler form on the total space X, the induced Kähler form on F will correspond to a general complex structure for E as a subset of Y. So again, it's a general Y in the deformation type and a general E on that Y. And we know, of course, well, of course, we're assuming we have a homological mirror symmetry statement between F and E. We obviously have the Lefschetz 1-1 theorem for E, and then that implies this statement that the classes of the Lagrangians, when we look in the corresponding part of the Leray filtration for the SYZ map, the SYZ fibration, is just exactly the perp of the complexified Kähler class. And so then this is equivalent to the statement I made above. Yeah, so of course we're assuming homological mirror symmetry for the two K3s involved, but that's expected. Yeah, so that sort of explains why when we did this monodromy calculation, the perp of this subset here is just monodromy invariance. It doesn't play a role. But let me also mention that sort of a corollary of this calculation here is that, okay, so the numerical K-theory of the entire category of the general fiber of this K-theory vibration is the same as the numerical K-theory of coherent sheaves on E, which of course is just the Picard group of E plus the H0 and H4 parts, which is a copy of the hyperbolic plane when you use the Mukai pairing, which corresponds to the intersection pairing on the K-theory of the Fukaya category. And so it tells you that since we just identified this this image of the K-theory with the perp, I'm sorry, what did I say? So yeah, so up here I made this assertion that the perp of the numerical K-theory is this image of the Picard group from the total space. And so I guess switching the perps, this image is the perp of Picky directs on the hyperbolic plane in the cohomology lattice of the K3. Now that's the usual sort of Picard lattice of a general fiber of the mirror family for E. So if you write down a K3 and you want to compute the mirror family, so going back to sort of Dolgotov, Lausanne, really the early days of mirror symmetry, people knew you should look at the family of K3s whose Picard lattice, generic Picard lattice, is this construction. The orthogonal complement, the Picard group of E directs on a copy of the hyperbolic plane. And I've sort of explained essentially how that would come about in terms of homological mirror symmetry. But as we said above, in this context, that's just the image of the Picard group of X, the total space of the KT vibration subject mapping to pic F. So it's the monodromy invariant part, Picard group of F, but the Picard group of F in general could be bigger. So the sort of moral is that this general fiber of the K3 vibration does lie in the mirror family of the K3E, but it sort of can be sort of more special than one would say. It's not sort of a general element. Okay, so yeah, so let me just quickly say how this works in the smooth case. So if we have a smooth Fano threefold and a K3 section, then we have, well, I hope we have, I believe this is true, we have some sort of Nerfa-Lefschetz theorem that the Picard map on Picard groups is an isomorphism for general E. general Y and E. And so by what we just said, the corresponding Picard group of F contains this perp, which is a rank 19 lattice. But remember, F is a K3 varying in a non-trivial family. We have this degeneration in the family. So the Picard group is bounded by 19, so it has to be equal to 19. And because they're both saturated, in fact, the Picard group is exactly this lattice, which is the mirror, the lattice for the mirror family of the K3E. So the usual Dolgorchev lattice. Okay, and so what it means then is that our fibration is pulled back from this moduli space of K3, so-called lattice polarized K3s, which generically have Picard group equal to this lattice L, and always have a primitive embedding of L Picard group. And then remember, we had one condition that the total space was log Calabi-Yau, kx plus d is equal to 0. So just using, so rephrasing that, we look at the Hodge bundle over this P1. So the line bundle whose fiber is just the H20, the space, the line of homomorphic volume forms on the fibers. Then, so that Hodge bundle has to be degree 1 on P1. So sort of it's always positive, the general semi-positivity of these bundles for varying families. Here it's sort of the minimal degree possible, degree 1. So that tells you that this map F can't be a sort of very arbitrary cover. And in fact, if you look at the possible moduli spaces here, so this moduli space ML has to, of course, be rational in order for such a map to exist. It has to be genus 0. Sort of a short list of those based on the K cubed of the Fano. And so just looking sort of case by case, you see this means that F has to be étale in the orbifold sense. And if you follow this through, you'll just recover exactly the list of mirrors to rank 1 Fano threefolds. So this actually completely matches with the classification in the smooth case. And these mirrors were already written down by Victor Przjalkowski. And I think this connection with the lattice polarized K3s is basically contained, is contained, in the work of Duran, Harder, Lomoseltsev, and Alan Thompson. Okay, so this is a very satisfying description of, the classification of Fano threefolds of rank 1 in the smooth case. So let's sort of see what changes in the Q-Fano case. And here I want to use the usual assumptions. So we'll assume that Y has only quotient singularities. So it's a terminal, has terminal singularities in general. Consider the model problem, you'd have a Fano threefold of terminal singularities of Picard rank 1. But here we'll restrict to the case where these are actually quotient singularities. So these are the threefold quotient singularities for quotient by a cyclic group Z mod RZ acting with these weights 1 minus 1A for some A co-prime to R. And we also further assume that we have an anticanonical section that has mild singularities. So specifically, so it will have a Duval singularity of type AR minus 1, so 1 over R1 minus 1, included as a linear section of each of these orbifold singularities on Y. So that's the sort of the best possible situation, but there are some sort of general theorems in this direction by Taro Sano and other people that you can sort of always deform to this situation with a few exceptions, I believe. Anyway, so the big point to make is that, okay, in this picture, one thing hasn't changed. This open Calabi-Yau, the complement of E, is still a smooth variety. And so really there, you know, this SYZ picture, I think, is really almost completely unchanged. So somehow the big sort of thing that gets us off the ground in terms of mirror symmetry hasn't really changed. But the thing that has changed, which is, again, it's not rocket science, but it's good to point out, this monodromy calculation. The monodromy at infinity is no longer going to be unipotent. And so let me just explain this from the point of view of homological mirror symmetry. So again, this is another thing I learned when I was a graduate student through many talks of Miles and others at Warwick. So let's regard E as an orbifold. So remember, it's K3 with some Duval singularities. It's an orbifold, if you like. And we have this action, the tensor product by this ample line bundle A, but now this ample line bundle is an orbifold line bundle. So it's, you know, it's not actually a line bundle on the actual singular K3, but if you work on the orbifold, it's a line bundle. Now, a basic fact here is that that derived category for the orbifold is isomorphic to the derived category of the minimal resolution. So this is just an instance of the Mackay correspondence, or rather the sort of homological version of that, due to, well, I guess in this context, maybe it's Caprano-Vassaro, but in more generality, Bridgeland-King-Reed. So again, remember, we expect under mirror symmetry, this corresponds to the action of the monodromy at infinity on the Fukaya category of the general fiber of the K3 fibration. But now it's just an easy calculation again that we know how to compute this monodromy on the complex side. So when we have one of these singular points, E, so it's a type A Duval singularity on the K3, and it's included in this threefold quotient singularity of Y, where the canonical divisor is not Cartier, it's just Q Cartier. Then if you look at the part of the derived category that's supported at the point P, the point P on the orbifold, or equivalently, if you look at the derived category of the minimal resolution, and you look at this part supported on the exceptional divisor over that singularity, then you get this basis of K theory given by the irreducible representations of the group, the cyclic group. And the action of tensor product by the line bundle is just cyclically permuting these. We're just tensoring by some non-trivial representation of Z mod RZ. So you get this sort of cyclic permutation, and you can see visibly this is not a unipotent action. So this is not unipotent, but of course the Rth power is unipotent. Okay, so that was the main point of my talk. And so let me just pause and ask if there are any questions. Everybody's still happy? Let's see if I can see the Warwick people. They seem to be happy.
There aren't any questions here in Warwick right now.
Okay, great. Okay, Tom is happy as well. Okay, good. So, all right, let's keep going. And so now let's just do some basic, you know, the kind of thing Duco was just talking about, just some basic questions about degenerating families on the complex side. So if you have a degenerating projective family over the disk, then using resolution of singularities and Mumford and collaborators, you can make a base change, and after which you have what's called a semi-stable resolution. So it's a resolution of the total space such that the central fiber is reduced, so multiplicity 1, and normal crossing. And then, you know, in this case, I think, I'm not sure if this is originally due to Clemens, but certainly Clemens computed explicitly that the monodromy is a unipotent operator on the cosmology. So the sort of conclusion is, given what we said above, in the Q-Fano case, you have a mirror K3 fibration over the affine line, which does not extend to a semi-stable family without a base change. So if you try to compactify this over the point at infinity, you won't be able to see this maximally unipotent monodromy point corresponding to a K, type 3 Kulikov degeneration of K3s. In order to see that picture, you'll have to make a base change. And so this is, something I put in my abstract because I think it's a really important question. And I hope people like Duco are able to comment on this. Is it going to be possible to classify such Picard-Fuchs equations? So you have sort of rigid local system with quasi-unipotent monodromy at infinity. Of course, if I make the base change in a sort of global way, I'm going to completely destroy rigidity. So I don't want to do that. But the question is, given the rigidity and then this sort of slight generalization of maximally unipotent monodromy points, are we going to be able to effect any kind of classification? And we know it's going to be complicated because we know the classification of Q-Fanos is complicated, but there's at least a clear path. Okay, and then here I just make some remarks about what you can do to compactify, and I believe, at least I believed when I was writing this down last night, that you can compactify in such a way so that, okay, the fiber at infinity is not reduced and it's not quite smooth with normal crossings, but you have this so-called divisorial log terminal condition, which would include, for instance, the kind of singularities we saw on the pair YE. So those singularities are sort of, from this point of view, the minimal model program, those are sort of on a footing with the smooth with plus normal crossing case. On a similar footing. Okay, and here I made this rather outrageous remark. I'm not sure I really believe it, but one could guess that the actual, the SYZ conjecture is sort of kind of a local conjecture in some sense. You're dualizing a torus vibration over a base. And so, it's a reasonable question. Is there some kind of local duality for these types of singularities that we saw in the setup for the Q-Fano? And if I had to guess, I would guess that, the mirror picture, you just change this character A to its inverse mod R. And then in this vibration, the component of the divisor containing the singularity has multiplicity R. And at least I've seen that in a few examples. And I really don't have much evidence for it, but that would be a sort of reasonable guess. And it's also something that presumably, if you are sufficiently adept with SYZ geometry, you might actually be able to produce a heuristic argument for this. Okay. Anyway, let me just quickly recap where we are here. So given the numerical type of Q-Fano, the mirror is a rigid family of K3s. You have this, the monodromy invariant part of the Picard group of the general fiber is given by this lattice, which arises in Dolgotov mirror symmetry for K3s. It has this quasi-unipotent, so not unipotent, but some power is unipotent, monodromy at infinity. And we completely understand the action on cohomology if we understand the action of tensor product with A on the K theory of the coherent sheets on the K3, on the original K3. So some of this is, I think this is sort of fairly soft information that you could certainly, in a sort of any program where you're trying to classify these, you'd have a K3 with a basket of singularities and you'd know exactly what this is. So you would have that information. And this Kx plus D equals 0, which is roughly speaking saying that the Hodge degree of this curve in the moduli space of K3s is minimal. Okay, so that's this big picture. And for the rest of my talk, I just want to discuss one example. And hopefully it's instructive. And I should also mention that, so I already mentioned I've done a lot of work on this problem with my graduate student, Christian Rodriguez. He's done a lot of calculations. This particular calculation, I worked with an undergraduate student, Patrick Lay, as well as Christian. So he's now a graduate student at Columbia. Okay, so this example, we take this Q-Fano variety, so it's the hypersurface of degree 5 in the weighted projective space P11112. So it's a Q-Fano threefold, Q-Fano threefold with a single #111 singularity. C3 mod Z2 acting by -1. If you look at the Picard group of the, oh, sorry, I should have written the resolution of E here. So it's given by this intersection matrix. So the initial polarization has self-intersection 5/2. When you resolve the A1 singularity, you get these two curves, self-intersection 2, self-intersection -2, meeting in a single point. So you get this matrix. Okay, at this point, I want to use the Horry-Vafa ansatz in this case. So in the case that we have a hypersurface, there's a very useful ansatz for the mirror due to Horry and Vafa, and I'll use that here. So a birational model for the mirror family is given by this function. This is the usual Landau-Ginzburg potential in the classical mirror symmetry on an algebraic torus given by this rational function. And you can sort of see how that is derived from this data we started. Okay, and so now this is some, as I said, birational model for the mirror family. I want to put it in a form where I can understand this as a family of K3s and analyze, for instance, the behavior at infinity. And what we do, so this is something I learned from Alessio. There's a way to do that. You first compactify completely naively in P3, but then, let's see, okay. Then you do what's called the two-ray game. So change the ambient toric space until you obtain a family of K3s with Duval singularities. And so I won't go into the details here, but here is the equation for that family. So it's a family of K3s of degree 6 in P1122 with coordinates U1, U2, V1, V2. And here W is the parameter in the K3 pencil. So W goes to infinity is a large complex structure degeneration. Okay, and so then there's just a little fun calculation, the sort of thing you can find in Dolgochev's work, where you have to resolve singularities of this family of K3. So here I want to emphasize, so this is one of Miles's 95 families, but it's not. This is not a quasi-smooth hypersurface in this embedding. So it has singularities that are not induced by the ambient space. But nonetheless, if you project onto the first two coordinates and resolve the base locus, which is in fact the free A1s that do come from the ambient space, then you get an elliptic fibration on your K3 with some singular points, in fact, just free A4 singularities. Like this, we have a type 4 Kodaira fiber and triangle of lines here. If you resolve, then you get this elliptic fibration with so the three concurrent lines, a type 4 fiber, an I15 fiber, so a cycle of 15 P1s, and then the remaining fibers are just I1s, ordinary rational nodal curves. And there are the three sections that come from the base locus of the elliptic pencil on the original singular K3. And then, okay, so using sort of standard techniques for K3s, you can see that the rank is, Picard rank is at least 18. It will be equal if the Mordell-Weil rank of this elliptic fibration is 0, so that the rank of the sections, the space of sections as a group is 0. And so this is something that Patrick did. He checked that using point counting So you sort of reduce mod P and you use the Veil conjectures, and you can check it using just counting points over FP squared, and so on. And so at the end of the day, we find that the Picard rank is exactly 18. And then it follows it's actually equal to this Dolbeschev mirror lattice, which let's call it L. Okay, and so the other thing I wanted to illustrate in this example is this fiber at infinity. There's supposed to be this sort of quasi-unipotent monodrome. So I wanted to sort of show that explicitly. And the only way I know how to do this is to resolve. I mean, of course, one could just compute the Picard-Fuchs equation, but I'm not good at that. I would appreciate assistance in fact. But anyway, so the fiber at infinity to begin with is just this union of 3 copies of the quadric cone P112 sitting inside this ambient weighted projective free space. And I've drawn here the picture, here's the sort of toric boundary of P112, and these 2 red curves are 2 sort of sections of the cone. Those are the double curves on each component. Then you glue them together like an orange in this way. Now the chart of the family at this top point, so 1, 0, 0, 0 in the ambient P3, looks like this. So just write it down. So just pass it into an affine chart, or if you sort of change coordinates, it looks a singularity like this. X, Y, Z is S times X plus Y plus Z plus higher order stuff that doesn't really affect the calculation. Okay, so that doesn't have a semi-stable resolution. Without base change, but if you make the base change S equals T squared, so a base change of order 2, as we expect, because we have a half 1 1 1 singularity, then one can just blow up. You see this, everything I've written down there is homogeneous of degree 3. So the exceptional divisor is a cubic surface given by the, I'm sorry, this should be, equals 0 there. Sorry. Given by this singular cubic surface as a triangle of lines at the boundary and 3 A1s at the 3 nodes. And then remember, because we made this base change, these double curves, so they're drawn in this sort of initial picture, the 3 double curves meeting at this triple point, there'll be a transverse A1 on there. And when you resolve those A1s, you find a semi-stable model. And I should say, the other triple point is already semi-stable. So there's a sort of well-established way to resolve that after the base change. So you just need to do an easy subdivision. Okay, so that's the sort of picture that shows you that this does seem to agree with what we said above, namely that the monodrome at infinity should become unipotent after an order 2 base change. Questions at this point? Okay, let me continue then. So now I want to look at this moduli space of these K3s polarized by this rank 18 lattice L. And then there's this well-established method. I guess it's originally an observation of Schroeder and Inose, and then it was worked out further by David Morrison, that if you have a lattice for the K3 that contains this sublattice, so 2 copies of the negative definite E8 lattice, then because of this relation between H2 of K3 and H2 of an abelian surface, they just differ by this term, then the period domain is just the same as the period domain for polarized abelian surfaces, where you sort of break off this E8, 2 copies of E8 factor. So we can just look, in fact, at moduli space of abelian surfaces polarized now by a rank 2 lattice. And that's something that was very classically studied. It's what's called a Humbert surface, or what's the same thing. It's the quotient of the Hilbert modular surface studied by Hertzebruck by the Galois involution. So there's an involution. So Hilbert modular surface parameterizes abelian surfaces with an endomorphism a subring of the endomorphism ring corresponding to a real quadratic field, and the involution corresponds to, the Galois action on that quadratic field. But anyway, so this is a very classical object, and it's a subset of, A2, the moduli space of principally polarized abelian varieties, but that itself is, of course, birational in this case for G equals 2 to the moduli space of curves of genus 2. But now, so we want to find these P1s in this surface, this moduli space, polarized K3s, these rigid P1s. And there's an obvious choice, right? So if you're looking for distinguished curves on moduli of polarized K3s, one thing you can do is just take the ones corresponding to rank 19 K3s. So you'll always have these modular curves on the moduli space of K3s given by just rank 19 families. But that's not what we want, remember. We want rank 18. And so we need something else. And in fact, what seems to provide the answer in this case is what's called the Teichmuller curves in MG. So let me very quickly review what that is. So if you take a Riemann surface C and a holomorphic one form on it, then you get a system of charts for the complement of the zeros of the form by just taking the one form and writing it as df locally. And those charts have the property that the transition functions are just translations, because of course this f is determined up to a constant. Now, this construction, so these are sometimes called translation surfaces, or well, actually, I don't know another name for them. But anyway, if you think about this picture, you'll see that, in fact, this gives you an action of SL2R on the Hodge bundle over MG. So the bundle with the fibers being the holomorphic one forms on the given curve, just by composition in these charts. So you take the chart, just post-compose with the element of SL2R, identifying, of course, C with R2. And so I guess, what's implicit in this is that you can go back and forth between the curve and the one form and this picture with these charts away from the singular points. Okay, and so then if you just take an element, C omega of lambda, you take the orbit under this action and you project it to MG. So notice that then the SO2 inside SL2R will act trivially. I mean, it just rotates the holomorphic form, it doesn't change the curve C. So you get a map from the quotient SL2R mod SO2, or what's the same upper half plane, to MG, and that's a holomorphic map. So the image of an orbit of a curve together with a one form under this SL2R action. Now, the bad news is this is usually dense in MG, it's holomorphic but not algebraic. But if the image is an algebraic curve, it's called a Teichmuller curve. And, because we're doing, mirror symmetry and such, maybe another point of view might be more helpful. And an equivalent condition, which is due to Martin Moeller, is that the variation of Hodge structures for this family of curves, we have a curve in MG, so we get a weight one variation of Hodge structures, just the H1 of the curves parameterized by C. I haven't given it a name. We have the Teichmuller curve in MG. We look at the variation of Hodge structures over that curve, so the H1 of the curves parameterized by that curve in MG. That contains rank 2 summand, such that the period map is a local isomorphism. And this rank 2 summand, if you think about the construction up here, it's just the real and imaginary parts of this chosen one form on the original curve. Yeah, and in the notation of Wiesweg and Zuo, this is called maximal Higgs. Maximal Higgs condition for the CHS. Whoops, sorry. So in this context, there's a classification of Teichmuller curves in M2 due to McMullen. In particular, they always lie on a complex surface. And in our case, this main invariant, the discriminant, which is the negative of the determinant of this lattice, is 5. And there are 2 cases for the type 1 curve. There's what's called the pentagon curve. So in this picture, the way that you get your genus 2 curve with a holomorphic form is you take 2 regular pentagons, you glue them along one edge, and then you identify parallel sides by translations. That gives you a surface of genus 2 with a single double zero, with a holomorphic 1 form with a single double zero corresponding to a vertex of this configuration. Yeah, and so the this maps an upper half plane to the MG. The image is given by the quotient by a triangle group acting on the upper half plane or Poincare disk. So you have a triangle in the disk with angles pi/2, pi/5, and 0. You look at the group generated by all reflections in the sides of the triangle, and you take the index 2 subgroup given by the orientation preserving elements of that group. You take the quotient, and you get an orbifold P1 with a Z mod 5 point, a Z mod 2 point, and a cusp. And so we expect, although we haven't definitively checked, that this is the mirror of this Q-Fano that we wrote down above. So certainly what we know is that our family has one orbifold point where the fiber is K3 mod Z5, one point where we have an ordinary double point A1, and we have this type 3 degeneration infinity, admittedly with this Z2 quotient, the Z2 issue. So this is, we believe, the mirror to this Q-Fano. And you can also check, for instance, that this curve is in fact Hodge degree 1 as we want. And then there's one other curve. We haven't done as much work on this one yet, but something called the decagon curve, which is even simpler maybe. You just take the regular decagon and again in the plane, and you identify opposite sides by translations. That now gives you a curve of genus 2 with a 1 form which has 2 simple zeros corresponding to the 2 equivalence classes of vertices under this identification. In this case, it's the hyperbolic plane mod triangle group for 5 infinity infinities. It's got 2 cusps and a pi/5 angle. Now here, we're not sure, but we believe this corresponds to the following element of Miles's list of 95. So you take Y10 in P11225. This has 5 half-111 singularities. Again, this is quasi-smooth. It's coming from the ambient space. So surprisingly, although you would expect the mirror to be much lower rank, because of course the Picard rank of E here is 6. And when you resolve, it's 1 + 5 is 6. The Picard rank of F, in fact, is 18 again, and you can show that the Picard group is isomorphic to L. And the reason is, again, in this family, the Picard group of the total space does not surject, in this case, onto the Picard group of the general fiber. So some of these classes in L are not monodromy invariant. So in fact, you don't have an L polarized family of K3s, but nonetheless, each fiber individually does have Picard group containing lattice L. And in the picture, when you sort of compute our mirror using the Horibata ansatz as above, what you find is you have a Z mod 10 Z orbifold point, an A1 point, and again, 1 cusp, and corresponding to the point at infinity. And what we currently believe is that this is a quotient of the decagon curve, where you've sort of forgotten the L polarization. You have to mark L. Here we don't have a marking of L. There's some non-trivial one. But I should say this second case is very much work in progress. But I did want to include it here because I wanted to give you some sense that it does seem like these tight Muller curves are going to play a role in this Q-Fano mirror symmetry, at least in the simplest case where you have a rank 18 family of K3s as the mirror. Okay, and so then I wrote down a little bit more about what else we know about this case, but maybe I should stop here since I'm already over time, and thank you for your attention.
Hang on, I'll pause the recording.